My name is Lauren Mack, and this is my analysis of Lab 1, Constant Velocity. The topics of this lab report are run down here. The purpose of this lab is to analyze an object moving at a constant velocity by using the observed change in position over time and comparing that with the predicted change in position over time. These results are modeled using a motion modeling software called Tracker and a computational model called GlowScript. The results seen in the predicted and observed results are expected to have linear relationships between the change in position and the change in time. But there is expected to be some deviation in the observed results due to human error and external forces. The system in this case is the marker, which is the object that we are analyzing or studying. The surroundings include any force that could potentially act on our system, but we are not directly analyzing or studying. The guiding principle of this lab is Newton's second law, otherwise known as the momentum principle. And this states that the net external force of a system is equal to the change in momentum divided by the change in time, as modeled here. To go further into derivation, one could derive the velocity update formula by breaking down momentum into its components of velocity, then rearranging the equation, getting the velocity update formula. Going even further, one could take the definition of velocity, plug in the velocity found from the velocity update formula, rearrange the equation, and get the position update formula. Now, what did we do in this experiment? What we did is we recorded a marker being rode in a straight line parallel to 1 meter ruler, which is our relative distance. We uploaded the video to Tracker and found the incremental positions by tracking snapshots of the object's motion compared to its relative distance. We then used the initial time, the change in time, and the initial position, all found in Tracker, to calculate the predicted model in GlowScript. And then we compared the graphs generated from both models numerically. In this Tracker analysis, what you can see here is the red dots, which are supposed to indicate the change of position of the center of mass of this marker. The points indicate the direction of the motion is in the negative x direction, which is why the points shown in the next slide are negative. I chose to set the axis, the pink axis, farther away from the edge because the marker was completely free of hand contact / external forces too, and this reduced inaccuracy. The initial time captured by Tracker is 1.233 seconds, and even though it's not zero, it does not matter much because it's the change in time that we use to calculate velocity and position. Other values seen here were used to calculate the initial velocity, which was used in the equation final position minus initial position over change in time. And in our GlowScript computation, to go further into our findings from the Tracker analysis, we found that mass is not relevant, so we set that value equal to 1, but we also used the position, the x position found in Tracker, the initial x position found in Tracker, and the velocity used in the previous mentioned formula. We then set time equal to the initial time found in Tracker, and we set delta t to 0.33 seconds, and we set t to be less than about 2.05 seconds, so that is our change in time. We then set the net force equal to 0 because constant velocity entails that there's no net force on the system. Now, what did we see in our observed and predicted graphs? What we see in our graphs is that the Tracker graph shows some deviations from a pretty straight line, while the computational model in GlowScript shows a perfectly linear model. The marker was somewhat linear, entailing that there was an applied force on the marker, that the applied force on the marker was enough to prevent the marker from slowing down significantly, while in the frame of the Tracker, leading to this somewhat linear graph without drop-offs. Now, getting into some possible errors that could have occurred in this experiment, there was a chance that there was unlevel camera positioning, which could have led to higher values or lower values in some areas. There's uneven initial force in the marker and inaccurate Tracker data points. So to get into the what ifs of the equation, what if the plus x or the minus x direction was flipped? In my case, the negative x direction was flipped, and if the marker was rolled in the positive x direction, the position magnitude would be the same, but the direction would be different. And looking at the observed force, is it equal to 0? The observed force of the model not being linear could indicate outside forces acting on the model. This could be forces from the surroundings acting on the marker in the x-coordinate, and there's no way to tell which components cause the interaction observed.